Okay, so now we're going to start with Unit 1 here. Um, looking at, I'm sorry, not Unit 1, Unit 5, which is kinetics. So, first question. So let's go ahead and move along here. All right, starting with some multiple choice. Now, there are review topics also under the 24-25 review sessions folder if you want to review kinetics that way, or you can just use your notes. But here we go with which of the following reasons correctly explains which of the following reasons correctly explains why one reason that increasing the temperature of a reaction increases its speed. So all the reactant molecules will have more kinetic energy. Large percentage of the reactant molecules will exceed the activation energy barrier. Higher percentage of molecular collisions will have the correct orientation. The order of each reactant will increase. So it's safe to say we can cross out C and D. So increasing the temperature makes all reactant molecules have more kinetic energy. The larger percentage of the reactant molecules will exceed the activation energy barrier. This is the more important reason because just because they're moving faster doesn't mean that they have enough energy to actually break bonds and form bonds. So when you're looking at that one, I think B is the better answer, but we can check the answer. Yes, it is B, as you can see there. The answer should be at the bottom of the slides there. So even though A, yes, technically is correct that they all have more kinetic energy, but what is really going to make sure that a reaction occurs is if they can break bonds and form bonds. So B would be the better answer here. All right, rate law. Rate law for the above reaction is determined to be K equals N2O5 concentration, or K times that gives you the rate. Which of the following options correctly identifies the overall order of the reactions as well as the molecularity of the rate determining step? So I guess first thing you should do is, based off of the rate law, figure out the rate determining step. Can anybody tell me the rate determining step? Based off of the rate law? No one?
The first one?
Yes, the first one, because here is your reactant that's in the rate law. Why is it going so slow? I don't like that. It's weird. Anyways, and since there's only one reactant, what would be the molecularity of that?
Unimolecular.
Unimolecular, so yeah, so your A is your right answer here. That would be correct. So it's first order, as you can see from the rate law, there's no, so that's a 1 there. And since there's only one reactant up there, then of course it's unimolecular. All right, here is a lovely graph. We've got concentration versus time graph. It's obviously not a straight line, so we know it's not zero order, but we can still look at the graph and find out a lot of information about it. So, sample of some gases of this N2O5 gas is placed in a sealed container, allowed to decompose. Concentration extracted over time results blah blah blah. Okay, the following represents possible units on the rate constant for this reaction. So basically, we do kind of need to tell if this is first order or second order. The easiest way to do that is to look at the half-life. So right here, when it's half the concentration, I don't know what I just did, that's going to be 5 seconds. And then at the next half concentration, right here, It's going to be 10 seconds. I don't know why. Come on, why's my tablet not working? All right. Well, anyways, marked there and marked there. So as you can see, the half-life is constant. It ends up being 5 seconds. So since the half-life is constant, I can't see what I'm writing because it's moving too slow, but so that means first order, and that means we've got seconds here, and it's 1 over m to the n minus 1 times the time to get the rate constant units. So this is just going to be 1 over seconds, so it should be A. All right, looking over here to the right, what we see here is a hydrogen peroxide and a Maxwell-Boltzmann distribution showing the activation energy line. So given the energy distributions on the curve for this uncatalyzed reaction, which curve would best represent a catalyzed reaction? So here, catalyzed reactions do what? Feel free to type or speak, I don't really care. I'm good with chat too, if you don't want to get on your mic.
They increase the amount of molecules that go, like that pass the activation energy.
Well, yes, that's going to be the answer, but really, like by definition, what does the catalyst do in terms of activation energy?
Oh, it lowers it.
Yeah, it lowers it, so that means more of the molecules are now meeting. So you're looking at the one that has the same graph here. So the curve hasn't moved at all. The only thing that should have moved on it is the line for the activation energy showing that more molecules now have met that minimum barrier because the activation energy was lowered. Hopefully, like, because as you can see, like the bell curve hasn't moved at all. So the answer is C. So this one flattened, this one, B got taller. This one also looks a little bit flatter. So you want to make sure that you want to make sure that your bell curve is the same on that one. The absorbance of cobalt-2, several different concentrations here was the molar absorptivity value. This is an easy plug and chug because the formula for Beer's law, we know absorbance, we know concentration. They tell us the path length is 1, so really we just have to plug it into the equation. So 0. You just pick one of the lines, it doesn't really matter. And you can easily calculate. So this is 0.025. And we should be able to get our answer. And it should work. Somebody do a different line, but we all should get the same one. And I'm getting 5.2, so I guess the closest one here, I'm going to go with C. But I can check one of the other lines real quick just to make sure. Yeah, so like if you do the third line, this one right here, the second one isn't particularly exact, but this one definitely gives you the 5.0 deal there. Okay. All right, so we have ammonium with nitrite, giving you nitrogen and water. Always look at your reaction. Which of the following is not a reason that increased temperatures increase reaction rate? So, so I guess you don't really need to look at the reaction for this one. The reactants will be more likely to overcome the activation energy. That's definitely a reason. Number of collisions between the reactant molecules will increase. Increase in temperature will speed up the molecules. They'll have more kinetic energy, so therefore B is also correct. They will be moving faster and collide more. Greater distribution will have higher velocities, so that's what I just said. An alternate reaction pathway becomes available at higher temperatures. That is the one that's not true, but what has to be added in order to get an alternate pathway?
The catalyst?
Yes, that would be the catalyst, gives you the alternate pathway and lowers the activation energy. So that really would be the one that is not part of the temperature increasing. Okay, so here another hydrogen peroxide showing at T equals 0 seconds, T equals 200 seconds, T equals 400 seconds. The above diagrams show that the decomposition, what is the overall order for the reaction. So let's see here. 200 seconds. There's 4, 2, so looking here at our data once again, we're starting out with 8, and then at 200 seconds we have 4, and then we cut that in half again at 400 seconds we have 2. That is showing a constant half-life. So this one was kind of hard to tell if you weren't looking for it. Always look for the half-lives because they like to use those. So constant half-life. Really don't like the way this is doing this, but okay. So this one's gonna be first order. Oh, a mechanism. Proposed mechanism for the reaction, which of the following is the rate law. Okay, so slow step is the first step. That's the rate determining. So all you have to do is look at the reactants and their molecularity. We have one NO2 and one ozone here. So each one should be first order. So I'm saying it's going to be A because they put a 2 here, so that's oxygen, not ozone. Oh, but this is a, yeah. And they put a 3 here, trying to confuse you. So just be careful. Make sure you look at all the subscripts. So this one should be A. Okay. An absorbance wavelength curve here. So this one probably pertains more to like the end of Unit 3, Beer's Law stuff, but Beer's Law, of course, goes with kinetics because we use it in the lab portion. So to determine the concentration of the copper nitrate solution of the unknown concentration was the wavelength that would produce the best results. So you have basically 2 major absorbance hills. One's around here. Of course, this one's higher. So you want to go for the maximum absorbance, which looks like it's going to fall somewhere between, right, almost directly between the 6 and 700. So that one should be C. So select the maximum absorbance wavelength as the one that, and that should be right because that's more in the orange, and orange is the complementary color of blue, if you don't remember that. But and the 400s are down there more by like blue and purple, so it wouldn't be the complement color. And let me see here. I gotta admit somebody. There we go. Okay. All right. Here we go with this one. They gave us the reaction, the rate law. Which of the following values, initial concentration of both reactants, would lead to initial reaction rate that is double that of the first? Okay. Double that of the first. So NO is second order up here by the 2, and then the O2 is first order. So we're looking at a combination that will double. Let's see here. So basically, looking here, you're going to square this and then times it by that to see. And it says initially we were starting with concentrations of 0.1. So let's calculate the rate of that. So 0.1 squared 0.1. All right. So we want to double the rate. So we need something, let's see here. Don't think it's going to be A or B because that should be squaring the first one and multiplying by the second. So we double the first one. So like 2 squared times this is 1/2. So that would be 4 times a half. And that one would be 2 times the rate. So concentration wise, this is double of 0.1 and this is 1/2 of 0.1. So I'm going to go with C, but I'm going to just check D just in case. But so if we were to square this one, that's 1/2 squared, which is 1/4, and this is doubled times 2. So 1/4 times 2 actually would not work. That would not be double the rate. These ones would be like 2 squared. Well, no, this is not doubled. This is 1.5 squared, sorry. 1.5 squared times 1.5 in terms of that. So that one would be right, but this would be doubling both of them. So it would be 4 times 2. This one would ultimately be 8 times the rate. So C is the correct answer. That one was fun. All right. I don't know why that keeps find my calculator. I'm going to take that out. There we go. There we go. Off. Stop making noise there. All right. The above reaction is run 3 separate times, varying initial concentrations. The initial rate is shown for each. What is the rate law? All right, so this is just pick the experiments kind of deal. And on a multiple choice question, you don't have to show your work, so you could just do it really fast. So here it's doubling and staying the same. So doubling for O3 and staying the same. So the O3 is going to be 0 order. And then here it's doubling from 1 to 3 for SO2. And then it goes from 0.3 or 0.075 to 0.3. So that one is 4 times. So SO2 is going to be second order. And so our answer then would be C, because you don't put in 0 order into the rate law. Okay, potential energy diagrams to the left. They're number 13 here. If the reaction is repeated under identical conditions but the catalyst is added, oh, that one's easy. So what happens to the hill when you add in a catalyst? It lowers the activation energy. So we're looking for the hill to go down. And C is the best choice. D would not be correct because they moved the product line on that one and made it endothermic. So just watch for little changes like that. Over here, slow step is the first step. So we know we're looking at these 2 reactants to be in the rate law. So that's going to be second order for NO2. So which of the following graphs actually represents the concentration of NO2 versus time? Well, we know second order, when you graph it versus time, it should be the inverse of the concentration one. That one should be your correct one that produces the straight line or linear relationship. So therefore, that would be the correct answer. So if it was 0 order, it'd be A. If it was first order, it would have been B. And then we can't really tell because they don't have any markings for D, but that's a concentration versus time graph where it isn't linear. So that's not giving us any good information there. All right, proposed mechanism, rate law, the overall reaction is known to have this rate law. NO2Cl is first order. What is the molecularity of the slowest elementary step? Well, if that's the rate law, which step needs to be your rate determining step? Anyone?
The first one?
The first one, yes. So there's only one reactant that makes it unimolecular, so it's got to be A. Since only one reactant, they have to have two reactants to be bimolecular, and then trimolecular isn't even a thing, so don't ever put that. And it's termolecular if there's actually three reactants hitting each other, and that's more rare. It's 36, still referring to the first part, which of the following would be the correct units for the rate constant. Since it is first order, the only one it can be is the 1 over time one. And for those of you, if you weren't here, I put this up at the beginning, but it's the molarity n minus 1 overall times the time. So if it's 1 minus 1, the m goes away. Identify any catalysts and intermediates present in the proposed mechanism. Okay, well, let's look over here. Cl is produced, and then it is consumed in the second step, subsequent step. So that is going to be a what? Anyone? No? Okay, I'll just keep talking. You can type if you want to, but no, it's fine. I got it. All right. So that one is going to be an intermediate. And the catalyst, if there were one up here, which I don't believe there is, you have to have it as initially being reacted, and then it gets produced at the end, where it's not a part of the overall balanced reaction, so it remains unchanged. So we're going to go with the intermediate is Cl, and the catalyst, I don't know why I just did that, but okay, go back. This one's B. I'm just going to do B. There we go. Oh, one that has a two-step mechanism, because we're looking at two hills here. Oh, this is part of that deal. Oh, let me go back. The rate determining step was the first step, right? Yeah, the rate determining step is the first step. We need to know that because the rate determining step should have the largest activation energy. So you really kind of need to compare activation energy lines. Oh, that is not stopping, and I don't know why it's not stopping. Don't really like that. Well, anyway, so it should cut off right here. This one, though, goes from here to here. So that one works where the activation energy of the first one. These ones look about the same to me, really. And these ones too. This one's a little bit shorter than no. This one's kind of shorter, I'd say. That one's definitely, this one's definitely shorter. So D is out. But I don't remember if they gave us information that this is exothermic or endothermic. Doesn't really look like they gave us information on that.
Oh, I think it says exothermic.
Oh, you're right, it does. I didn't read the first line, so read the first line. So we want it to be, it's got to be A or B. So it's definitely going to be A is the better choice. That is correct. Because D and C are endothermic because their product lines are higher. Now you can click on this link and there's like a whole page of more multiple choice questions for kinetics that you can look at. And the answer key is at the end of that document if you want to look at it. All right, so now it looks like we're going to get into looking at some FRQs. So hang on one second. I'm going to try to fix my tablet so it's not behaving weirdly because I'm going to have to write a lot. So hold on one second. Or use this as a time to go to the bathroom or something. Okay, so starting some FRQs here. We have our reaction, data gathered. They gave us time versus concentration. How does the rate of appearance of NO2 compare to the rate of disappearance of N2O5? Well, justify your answer. Okay, so if you look here at your reaction, Remember, rate of appearance and disappearance is going to be so 1/2 for the change in the concentration of the N2O5 over the change in time. So this would be basically, that part is like the rate for the N2O5 and how it compares to the other one, which would be 1/4, the change in the concentration of the NO2 change in time. So that would be the rate for the NO2. So basically, so 4/2 times the rate of N2O5 here. So basically, this is 2 times the rate of the NO2 concentration. So the rate of appearance of NO2, oh, well, I guess, so the rate of appearance of NO2 compared to the rate of disappearance. So I would say the rate of appearance, in this particular case, you cross it that way, so it would be like 1/2 the rate of appearance of NO2. Well, no, is the rate double the, that's right. Okay, I'm saying it right. Let me erase that. The rate of appearance of NO2 is double. I thought I clicked the pencil. There we go. Never mind. The rate of appearance of NO2 is 2 times the rate of disappearance of N2O4 or N2O5. And you can use this as your justification, or you could just talk about, you know, the 2 moles to the 4 moles there up in the reaction. You can note that too. So NO2 is 4 moles compared to the 2 moles of the N2O5. Therefore, it is appearing at double the rate of the N2O5. So the reaction is determined.
So can we solely use the mole ratio as our justification for the answer?
Yes, I believe so.
Thank you.
So the reaction is determined to be first order. Overall, on the axes below, create a graph. It doesn't look like we have axes here. Some function of concentration versus time producing a straight line. Label it and scale it appropriately, but we don't really have a graph here, but you can, you know it would be ln of the N2O5 because it's first order, and first order, in this case, the time in seconds. And the graph is always a -1. So k is, or negative k will equal the slope for that. If they had you graph it, of course, you would scale it appropriately, and they gave you good time intervals here, and you can change these over to ln and get those values. I don't think they're going to make you graph anything, though, on the FRQ. I think they will give you graphs to analyze. So this must be a much older question. What is the rate constant for this reaction? Include the units. Well, since it's first order, we can just use any line, doesn't matter, and all we need to do is use the first order equation, which is what? ln concentration at time t equals -kt plus the ln of the initial concentration. So ln at time t, I'm going to go with this line right here, -k times the time, which is 500 seconds, plus the ln of the initial concentration, which was 0.250. Very good. And we can get our rate constant. So if somebody wants to do a different line and can check the answer, but I'm getting, see here, 3 significant digits for each, so I'm going to go with 3, so I'm getting 5.49. What happened to my pen? It went away. 9 times 10 to the -4. First order would be 1 over seconds. And remember those units for the K is always like one single point on the FRQ if they have it there. So make sure that you always put in those units correctly. All right, what would be the concentration at 1500? Well, now that we know the K, you can plug and chug for that one. So I'll do this one down here. So we have ln time t here, and we have -5.49 times 10 to the -4, 1 over seconds, times the 1500 seconds, plus ln of the 0.250, like so. And we can solve for the concentration. -4 times 1500 plus ln 0.25, and got to e to the x that one. Make sure that you do that. So I'm getting concentration at the 1500 seconds to be 0.110. It comes out like 0.097, so molar, don't forget your unit. And 1500 is in between these two values here, so you can see, is our number in between those two values? Yes, it is. So that as a way of double checking to make sure I did it right and got my calculation correct with the calculator. Okay. What is the half-life? Well, that's easy one. T half-life is equal to 0.693 over K. That's on the formula sheet. Plug in the K value in there, and we can get our half-life. And I'm getting, let's see here, where did my thing go? Did you? Sorry, my tablet doesn't want to stay connected. All right, here we go. So I'm getting a raw answer. This is a raw answer, so I'm going to go with 3. I guess I'm going to go with 1260 seconds, okay, for the half-life one. And once again, I can look here because we want it to be 0.125 as the half, and it's going to be somewhere in between those two values, so that one definitely makes sense too. With the addition of a catalyst, increase, decrease, or have no effect on the following variables, justify your answers. The rate of disappearance for our N2O5, which is our reactant. If you add a catalyst, catalysts speed up the chemical reaction by lowering the activation energy. So yes, I would say this one would increase the with the addition of the catalyst, increase, decrease, or have no effect on the following variables. I guess it's not going to. Oh, the rate of disappearance, yes, would increase. That's what we're going for. Because it's going to speed up the chemical reaction, because catalyst does that by lowering the activation energy, so it will go faster, so your reactants will deplete faster. The magnitude of the rate constant. The catalyst actually, addition of the catalyst would be part of the rate law, because that's usually concentration dependent, so I'm going to say that's not going to have any effect on the K constant, the magnitude of the K constant, because we always put the catalyst in as part of the rate law. They are concentration dependent. So I would say this would have no effect. It's really half-life. Half-life is speeds up the chemical reaction with the catalyst. That should decrease the half-life. If it's going faster, it takes less. It's going to take less time to, but it's still going to be a constant half-life because it's first order. It's just going to take less time to get to the halfway mark, which would be the 0.125 concentration, since the reaction is moving faster. So I would say yes, that one would decrease. This one would decrease the half-life. So this would increase the rate of disappearance, have really no effect on the rate constant, and decrease the half-life. I don't think they're going to ask you those type of questions, though. This one must be an old FRQ. Hold on, I need my pointer to be able to advance the slide. Okay, now I can point. Let's see what they say. Oh, I wrote all over this. Now we can't see what they say. Increase, no change. They're saying that 3 was no change. I disagree with that, though, because if you're increasing the rate, you're going to get to the halfway point faster than you would have beforehand. So, anyways, okay. As you can see, somebody wrote out the answers here. All right. Oh, now I have to erase everything? This is going to be a pain. I don't like this tool. I'm not sure it will let me. Nope. Doesn't do it like the smartboard. Sorry about this. Didn't realize this is how it's going to work. That it shouldn't carry over to the next slide. And like I said, I don't really think they're going to make you graph it, but like it tells you that this one is first order. So you would want to, if you're drawing this out, you would just want to make sure that you, at the, tells you that the half-life is 1200 seconds. So at 1200 seconds is where you would need to make sure that that hits the 0.5 mark. And at the 0.25 mark, it should be about 2400 seconds, and it would be a decay curve looking problem. And they're not going to ask you to do an instantaneous rate. I don't think they're going to do that either. So I wonder if I hit trash it. Oh, that'll clear it. That'll work. Okay, we'll do that next time. So I'm going to move on from this one, and we'll go on to the next one, because we want to get to some equilibrium stuff soon too. All right. So here, chlorofluorocarbons are byproducts of many different processes that are known to be dangerous to the environment as both a greenhouse gas as well as an agent for ozone. The accepted mechanism, write out the full reaction with the above elementary steps. Identify catalysts and intermediates. Describe 2 ways by which a catalyst can reduce the activation energy of a reaction. And both elementary steps in the above are exothermic. On the axis provided, draw the potential reaction mechanism that supports this. Okay. They're not actually giving us a rate law here, are they? Chlorofluorocarbons, it's both the greenhouse gas accepted mechanism. Well, we can write out the full reaction. That's not a problem. We can do that. So here, CLO, that's an intermediate. That will cancel. The Cl, these are catalysts, so that's not a part of the overall balanced reaction. So it's going to be O3 plus O gives us 2O2. So that's your overall balanced reaction. Catalysts versus the intermediates there. Describe two ways which a catalyst can reduce the activation energy of a reaction. Well, it lowers the activation energy by orienting the particles more favorably. I know orientation. So therefore, when they orient them, and a lot of times, especially with your heterogeneous ones where you have the like metal platforms, it is kind of like a loading dock, which allows the particles to line up correctly so they can break bonds and form bonds. But I'm not really sure what the other one is. I haven't ever had to do that, but we could take a look and see what they have. If they have it here in their answer key. I can. I'll have to go to pointer. Stupid. Here we go. Pointer. Let's see. Let's get to that slide. See if it's in the. Here. Oh, no, they don't have any. I guess it must be an older question. Once again, there's nothing here. So orientation would be the only one I could pick out for that for you. But like I said, that would be just a way of describing allowing the particles to line up so that they don't have to have as much energy. It's a way of connecting them and putting them together. It says both of them are exothermic, but it didn't ever tell us which one was the rate determining step. I mean, I'm assuming the first step is the rate determining step because I've seen this mechanism before, but it doesn't actually tell me that the first one is the rate determining step. Obviously, with the chlorine being added as a catalyst, that is making it move faster. So I guess that's why we're supposed to assume it's the rate determining step. So the rate determining step, both are exothermic. So you would just want to make the first hill bigger. And it goes lower here. And then this one, I need to switch back over here. Let me erase this. Pointer options. Eraser. I'm going to go over here and use their ink. Draw. So we have this one higher, this one lower, and then activation energy. So higher hill for the first one. As we're saying, this is the rate determining step, so this one would be a little bit lower. But this line should dip below the first line if they're both exothermic. So that would be a way of doing that. So, all right, clear all my drawings. Now that's working better for me. Pointer. And move this. Let's see if I can move this down here closer. That will be helpful. Okay. Now we have another Beer's Law looking like graph here. Sorbents solution concentration is 0.219, determine the molarity of the solution. In this particular case, where they don't give you a best fit line with the y equals mx plus b, then we can employ or use the like A1 over C1 equals A2 over C2 idea because they're proportional, using the Beer's law equation. So if I know, I can find a point on here that pretty much crosses almost right directly in the middle, like right there. Probably could use that one. Or this one right here is in the middle. Yeah, I kind of like that one. So in that case, this is what I would do. So this is 0.300, so that's going to be half. So the concentration 0.400, and this is 0.25 for my absorbance, 0.219, and then we can look for the second concentration. So this is what you do when they don't give you a best fit line. I wouldn't try to estimate it. I would find a point that makes it more accurate. So I'm getting C2 0.0. What the heck just happened? 350 molar. So, second student performs the same experiment. There are drops of water in the cuvette before the student adds the copper sulfate. Does this result concentration for the unknown that is greater than, less than, or equal to the concentration determined in part F? So if they add it to one that has water already in it, what's going to happen is it's going to measure a lower absorbance because some of the water will dilute it, and so you'll get a lower absorbance, and therefore, due to Beer's law, where absorbance and concentration are directly related, the resulting concentration, so the resulting concentration of your copper sulfate is going to be lower. And that's what you would justify your answer, but you need to cite, don't just say it's diluted. So therefore, no, you need to talk about that the measured absorbance then would be lower through Beer's law being directly related. Cite the equation that A and C are directly related. Therefore, the calculated concentration of your copper is going to be lower. And then we can trash that pointer and move on. All right, so here we have, I'm going to get rid of your options. It's bothering me. Nope, it's not allowing me to erase. Okay, I guess not. All right, we'll go back here then. Nitrogen dioxide, we have 3 graphs here. It says 2 graphs that follow are derived from the original data. Explain how the graphs indicate the reaction is second order. Well, if you look here at this graph, this is the one that's showing the linear relationship. So therefore, how the graphs indicate the reaction is second order. So 1 over, or the inverse of the concentration of the NO2 shows the linear relationship when you say this graph versus time. So 1 over the concentration of NO2 versus time graph gives the linear relationship. Therefore, it would be second order. Writing the rate law, rate equals K times NO2 squared. So that would be your rate law. Oh, looking at the proposed mechanism. Is the rate law described by mechanism 1 shown below consistent with the rate law you wrote in part B? Actually, if you look here, the slow step is the first step. We've got bimolecular here. So yes, this would be, because the reactants are bimolecular, it would make it squared. So yes, it would be consistent. Now, if we looked at the bottom one, is the rate law described by mechanism 2 consistent? We have the fast equilibrium, the slow step is the second step, so that's where you would need to do the substitution. Okay, so here's the rate law for your slow step, your rate determining step. But if we do the substitution, K equals the concentration of NO2, N2O4 over our reactants squared. So equilibrium, this is like KEQ, equilibrium K. I do it the equilibrium way. I know you can do it the rate way, rate forward, rate reversed. And then you would just show that this is going to substitute in. So this part substitutes in, I'm sorry, it shouldn't be K, this should be the concentration of N2O5. That part substitutes in your rate constant times the equilibrium constant. This turns into a new K, and then times the NO2 squared gives us the rate here, like so. So both of them you would say yes to go with the proposed rate law up above. Both of them would. All right, so trash, clear my drawings, move on, next slide. Okay, so this one, blue food coloring. Hey, we did blue food coloring. Based on the graphs here, what is the order of the reactant? Well, that's going to be this one, obviously, because it has, oh, my pen thing switched over again. Sorry about that. That's weird. Anyways, it's the natural log of the concentration versus time graph. That one is going to be straight linear, so that one is not going to let me erase that one, of course. So anyways, this one right here is the linear relationship. ln of absorbance versus time graph is a linear relationship, and therefore it's going to be first order. Now it says the reaction is known to be first order with respect to bleach. So we know now this is the blue dye, because the one that's being absorbed is going to be the blue dye, since it's the one that has a color that's going to fade. But bleach, they're also telling us that that one is first order, so that one would be like a 1 there. Second experiment, the student prepares solutions of the food coloring and bleach with concentrations that differ from those from the first. When the solutions are combined, the student observes the reaction mixture reaches an absorbance near 0 too rapidly. In order to correct the problem, the student proposes the following 3 modifications: increasing temperature, increasing concentration of the food coloring, increasing the concentration of the bleach. Circle one proposed modification above that could correct the problem and explain how the modification increases the time for the reaction mixture to reach an absorbance of 0. So, if it is being bleached too rapidly, that's what it says. Near absorbance is going to 0 too rapidly. The bleach concentration was probably too high to begin with, or the blue food coloring concentration was too low to begin with. So I'm going to circle the middle one. That's the one that I would change. I would increase the concentration of the food coloring, because it doesn't give me an option to decrease the bleach or the color or the concentration of the bleach. It doesn't give me that option. Increasing the temperature is going to make it go faster, makes the particles move faster. We know all that, so that one isn't really going to help us. So if you increase the food coloring concentration, it will take longer for the bleach to react and fade the color, and therefore it will take longer to get the absorbance of the blue food coloring to 0. And this one, I believe the scoring guidelines are attached to the slide, so you can look at their exact wording on that one. Another experiment student wishes to study the oxidation of red food coloring with bleach. How would the student need to modify the original experimental procedure to determine the order of the reaction with respect to the red food coloring? Well, obviously, they would need to change their absorbance value on their spectrophotometer, because we know that red is going to absorb a different wavelength of light than the blue is going to absorb. Remember, blue absorbs mostly like the red spectrum. I'm sorry, the orange spectrum. The complementary color of red, I'm not exactly sure what it is, but you would need to change the wavelength so it would maximum absorb for the red. So that would be one thing you would need to modify in order to be able to track and get the data for the red food coloring. I'm sure there's probably a couple other options, but that's the one that came to my head immediately so far. Like I said, the scoring guidelines I think are attached to this one, so you can see what they say there. This one was like from 2018, or what did it say? It said it on the slide. 2015, so it's a little old, but yes, the scoring guidelines are out there. This one's from 2014, so we have half-life of the cis-2-butene, trans-2-butene reaction, and various conditions here shown in the table. All right, so the half-life telling us right here, initial pressure of the cis-2-butene, looks like these are in gases, volume, temperature, initial pressure, half-life is 100, initial pressure, half-life is 100. The only thing that gets changed here for this one is the temperature. So therefore, if we're looking here, that looks like why the half-life might be affected, because the temperature would change the rate constant, and the rate constant then would change the half-life, I suppose. So the reaction order is first order. Explain how the data in the table are consistent with a first order reaction. Well, the first three half-lives are the same, so that's showing it's consistent at the same temperature. Therefore, a consistent half-life means that the consistent half-life means it's first order. So you can easily stick to that one. Okay, I'm gonna erase these. All right. Calculate the rate constant. Okay, for the reaction, include the appropriate units. So all you got to do is do the K equals 0.693, not K, T half-life. That's T half-life, and then K's on the bottom. And then you would just put in the 100 seconds here, and you can calculate K. So 0.693 divided by 100, right? Am I doing that right? 100 seconds. So that's 6.93 times 10 to the minus 3. It's first order, so 1 over seconds. Is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Justify your answer. So rate is going to equal K times the, well, in this case, I guess we would go with the partial pressure of the cis to butene pressure, because pressure is like considered a concentration. I suppose I don't think they really want you to calculate the concentration, although they do give you volume, they give you temperature, and they give you the pressure, so you can find the moles using PV equals nRT. And then if you wanted to find the moles, you could go with the concentration, but I think we could get the rates this way anyways. So 6.93 times 10 to the minus 3 times the initial one would be 300 versus the 6.93 times 10 to the minus 3. For the trial 2 would be 600, so looks like the rate's gonna pretty much double. So you would say it's initial rate for reaction 1, that would be less than the initial rate for reaction 2. I guess suppose you can show the math this way, or you could just say that because it's first order, since the partial pressure is doubled, which is essentially pretty much its concentration in the same volume, therefore it's going to double as well. The half-life in the reaction in trial 4 is less than the half-life in trial 1. Explain terms of activation energy here. So since the temperature is higher, that means that more of the particles have reached the activation energy barrier and can have effective collisions, therefore speeding up the chemical reaction. That's what I'm going to go with there. For that one, like I said, you can go to the scoring guidelines if you want to look at their wording on that, but that's what I would probably say to that one. And it's now 11:09, so might have to switch over to equilibrium. I don't know how many more slides are in this one, but we can check it real quick. Here are all drawings. Let's see here. And I don't know if it'll let me. Let's see here. We did this one right. So there's a couple more here in this particular one you can look at. Looks like they all have their, they have a link here in the bottom so you can go to this guidelines and check them out to get a little bit more, but we pretty much covered most of the kinetic stuff here one way or another. So let me minimize this one. And here's unit 7, equilibrium stuff. I'm gonna go here, bring up my PowerPoint, get rid of this one. Don't save that one. And go to equilibrium. And this may also help you review a little bit for acids and bases, because a lot of the equilibrium concepts work for both. So here we go. Take a look here. Once again, these are posted. Yeah, I wish it would pop up and tell me people are there. Okay. All right. Unit 7. Here we go. All right, so manipulating K, remember if you multiply through by I don't know why it's distorted, but you multiply through by, how was it manipulated, this one? Original K. What is the new K? So original K is K1, new K 1 over K1. I suppose we would just say it was multiplied by 3. Everything was multiplied by a factor of 3 in the equation. Because and it was flipped because we did the reciprocal here. So flipping it is a reciprocal, and multiplying through by 3 to raise it to the third power. So that's how it was manipulated. It was reversed and multiplied through by 3. So 1 over 0.2 raised to the third power. I don't understand this slide. We're going to move on from that one. Okay, well, somebody made that up. So we're going to go with the actual questions now. Saturated solution of sodium phosphate. Okay. 0.3 molar. What is the molar solubility of sodium phosphate? Okay, that's a good question. I like this one. Let's go here. Come on. Why are you not? Hold on, let me fix this. They didn't put anything there for those notes anyways. We're on the slide. Wait for my current slide. Not letting me get to my annotated. But there it is. Okay, now I can reach it. Okay, so we have 3 over here in our compound, 3 sodiums. The concentration of the sodium is 0.3. So if you're thinking about molar solubility, this reaction, when you dissolve it, this is the solid, you get 3 sodium ions for every 1 phosphate, like so. So the 3 sodiums here, this is the 0.30 molar. And we know that molar solubility is based off of the original formula unit. So that would be like 1/3, because this is like 1 to 3 ratio. So we would divide this by 3. So the molar solubility would be 0.1. Okay. Oh, we need trash. Clear all drawings. Move on. It's not letting me get down here to. What the heck? Why won't you go away either? And I don't know. Okay, there. Finally got rid of it. Okay, now we can move on. Oh, now it's going too fast. Okay. All right, we're now on the right track. Okay. The reaction above it's at equilibrium in a closed system, so it's forming a complex ion. Which of the following will happen immediately when the water is added? Rate of the reverse reaction will increase. Both ions will increase in concentration while NH3 decreases. And the reaction will shift to the right. Nothing will happen. Adding water does not cause any changes to the equilibrium system. Huh. They didn't really give me. Adding water will decrease the concentration of everything, but they didn't really give me an idea of where the constant is. So we know water is a pure liquid. So I'm just going to, in this particular case, they didn't give me any other information, so I won't know how the dilution works. I'm going to go with D on it. But let's see what they say. Okay. Discard. There we go. The rate of the reverse will increase. Okay, they're saying it's A, so we're supposed to know that it's going to dilute. And like I said, it's not telling us the K is super large. I'm assuming it's super large because it is a complex ion and most of those are super large. I don't really like the way this is phrased, but in that particular case, if K is super large because it's complex ion, that means that the left side ions and their concentrations would dilute faster than the right. And that's why it would essentially be removing the ions on the left faster than it is on the right in terms of concentration levels. And that's why essentially removing makes it shift left. So I think that's why the answer is A, but I don't really feel like it's given us enough information for that. But what do I know? Let's see here. Okay. Given the above, oh, they finally give us some K values here. What would the equilibrium constant be for the following reaction? So now we have to look at manipulating it. So we have 3 COs. So it looks like I need to multiply this one by 3. So this is going to be raised to the third power. Looks like this one needs to flip and be multiplied by 2, right? So this is going to be 1 over 1.4 squared. Is that right? Two CO2. Why is it giving me 3 COs? Oh, never mind. I don't need to multiply this one by 3. Because when we multiply this one by 2 and flip it, this is going to be 1 CO and that's going to be 2 COs added together. So we don't need to do that. Like, none of these answers were matching what I had over here. So basically, I'm going to have 14.5 times 1 over 1.4 squared. Hey, and that one is C. That one makes sense. That one actually works. Okay. Zinc iodate dissociates in water, and they gave us KSP. What is the approximate molar solubility of zinc iodate? So here, this is KSP. Once again, in the wrong pen. This is going to be, this is a 1 to 2 ratio. 1 to 2 ratio is going to be x times 2x squared, which means we're going to get 4x to the third equals KSP. Plug in KSP. And like I said, on a multiple choice question, you don't really have to show your work, so you can just do it mentally. 4 negative 6 divided by 4. And then we got to do the cube root. So I need my math one. So I'm getting this answer for x. Actually, technically, this is what popped up in my calculator, but that's the same thing. Which of the following solutions would zinc acid iodate be least soluble in? Well, I can point that out to you right there. That is known as the common ion. So it is going to shift it left and make it less soluble. So we're going with B as the common ion. Beaker of saturated zinc iodate is left out overnight. We're going to safely assume some of the water has evaporated then, assuming the temperature remains constant. Which of the following options correctly identifies as the changes in zinc and the mass of the zinc iodate present in the beaker? So if some of it evaporates, that means you have less volume per particles, so it's going to shift left. If it shifts left, then this mass should increase. So, and then the saturation point looks like is not going to change for the zinc. So because it shifts left and makes some of the zinc iodate precipitate out of solution, now the concentration of the zinc per the less volume will be back to its original saturation point, and that's why it says no change here for C. Because you lost some of the water, so some of the zinc precipitates out. Now it's back to its original zinc concentration, which is the equilibrium point, that saturation point. And trash. Okay. Which of the following reactions are the numerical values of Kp and Kc the same? Oh, this is a good one. I like this one. I want to, oh, let me change colors because I'm not on that one. Okay. So in this particular case, that was that Kp equals Kc, or is it Kc equals K, I don't remember. Anyways, RT to the delta N. I don't remember which way these are, but if the delta N is 0, then that goes away and your Kc equals your Kp. So you're looking for the same number of moles of gas on the reactants and products. So same number moles gas, reactant and product. So this is 2 and 1 equal 2, so that's out. This is 1 and 2, so that's out. This is 4 and 2, that's out. 2, it looks like it's E. So that's 2 and 3, so D's out. So that's what you're looking for that particular problem. All right, moving on. Okay, sample of H2S gas is placed in an evacuated sealed container and heated until the following decomposition reaction occurs at 1000. Kc is kind of small here. So reactant favored reaction, which the following represents equilibrium constant. Everything's a gas, everything should be included. So products over reactants raised to the second power, raised to the second power. So looks like A, C, and D are out. And yeah, these ones are switched. So it's products over reactants raised to the power of the coefficient. Oh, here's some Le Chatelier graphs. Let's see. Which is line graphs would best represent the change in concentration. It evolved over time. Okay, so K is less than 1. So let's see here. They're all starting with H2S. So H2S is fine, but it is reactant. Kc is less than 1 though, so it shouldn't have, it should have more of reactants than we do products, since the Kc is 10 to the minus. Which of the following graphs best represents the change in concentration of the various species involved over time? Double that, double, single. Well, this one's out, obviously, and that one doesn't make sense at all, and should be kind of a leveling off. I don't know about these weird ways that they're drawing them, but still at equilibrium it should be more reactants than it is products. I don't understand this graph, but in terms of molar relationships and things, this is 2 to 1. So this one, the slope looks like about 2, this is about 2, and that's about 1, half of it. So based off of the mole relationship, I think that's the best answer, but still it's not making sense with the Kc being less than 1. You should still have more reactant than you do product. So, but let's take a look and see what they say here. Now I have to go to the pointer. What did they put for their, come on. They're saying it's C. Okay, that's what the one I put, but it does not jive with the Kc value. Okay. Which option best describes what will immediately occur to the reaction rates if the pressure on the system is increased after it's reached equilibrium? So for pressure, you are looking at the moles of gas. So if we're looking at pressure, come on, pop up. Come on, why are you not? Thank you. Finally. All right. So here's 3 moles, so 2 moles, and we're increasing the pressure, so it should shift left towards the side with fewer gaseous moles. That means the reverse reaction should increase. Which option best describes immediately occurs? So the reverse should increase. Neither rate toward, so that one's out. We'll get rid of D. Both are not going to increase. So rate of the forward will increase, rate of rear, so it's got to be C. Rate of the forward decreases while the rate of the reverse increases because it's shifting left, going towards the reactants to fewer gaseous moles to relieve, get back to the same pressure that it once was. All right, here is another complex ion one. We have gold plus cyanide, making the complex ion. Delta H is positive, so it's endothermic. We need to know that. The above systems at equilibrium cause an immediate increase in the rate of the reverse, so going that way, rate of the reverse. Adding some water, once again, dilutes this side faster than that one, so yeah, that one should shift. If you're adding in this, though, you're really adding in the gold. So that would, if you add in the gold, it's going to go to the right. Pressure is not going to affect this system at all because none of them are gases. If you increase temperature, heat is over here because it's endothermic, it would shift it to the right. So adding water to a system with complex ions, this side dilutes faster. So basically, it reduces the concentration of those ions faster. So it's like essentially removing them, and that's why it shifts left. So the answer would be A. I don't know how many complex ion problems they'll give you, but anyhow, just so you know, that's kind of how that works. All right, we're on the right slide now. Okay, using the above information to determine the equilibrium constant. So it looks like they reversed it and multiplied it by 2. So, because 2 COs here, 2 COs right here, it's been reversed, multiplied by 2, so 1 over 5 times 10 to the minus 3 squared, whatever number that one turns out to be. I'm getting D as the answer. So it was... Okay, partial pressure of each gas above are these 3 values. It says it's at equilibrium, so this is just a plug and chug. All you need to do is put it into the expression. And like I said, on these multiple choice ones, don't even bother with like doing extra work. NO2, NO, and O2. So O2 is on the top, 0.2. NO, 0.3 squared. And then NO2 on the bottom. Just quickly fill that in, or do it mentally, or do it in your calculator so you can move on quickly through the multiple choice. And I'm getting A as the answer. Three gases are injected into the sealed container. Kc is above 1. Initially, 3 gases are at 0.1. Which of the following must occur in order for the reaction to reach equilibrium? Oh, fun. Okay. Well, they gave us initial concentrations of everything, so this is a Q problem, if you didn't recognize that. So it's going to be 0.1 for this one over 0.1 for that one times 0.1 squared, and this is going to give us Q. We need Q to compare to K to know which way it's going to go to reach equilibrium. So I'm getting 100 for Q. So Q equals 100. That means that K is less than Q. It means it's going to shift left in order to get to equilibrium. So A is out, and B, B is out too, because they're not all going to increase and they're not all going to decrease because it's shifting one direction to get to equilibrium. But the concentration of the reactants must increase while the product will decrease. I'm going to go with C for now, but I'm going to read the last one just in case. So it's opposite. Yeah, so it's got to be C, since it's got to shift left to get to equilibrium. Remember, when you're given initial concentrations with everything, you have to do a Q problem. All right. So pointer, trash, drawings, move on. Okay. Here they've given us delta H, a solid producing 2 gas products at 298, and they gave us the KC. So they gave us lots of information on this one. We see we have, that's K is less than 1, and we're endothermic, so heat's over here. All right. So calculate the concentration of the NH3 gas at equilibrium. Some solid was placed in a sealed evacuum 250 milliliter flask. The above decomposition reaction is allowed to reach equilibrium. Let's see here. All right, so Kc basically is going to be the concentration of the H2S times the concentration of that. And there's only the 2 gases in it, so there's nothing on the bottom. I guess you could put it over 1. But the other thing you would notice, this is 1, this is 1, this is 1, so everything is 1 to 1. So 9 times 10 to the minus 2, basically this is like x and x, so it's going to be like x squared. So we can square root it to figure it out. So it looks like the answer should be B. I'm getting 0.30 molar. If some additional NH3 is injected into the flask, which of the following option correctly predicts the reaction shift? So if we're adding this, that means it's going to shift left. And we don't have to do KQ here because it's not part of the answers, but if we're adding to the products, that means Q, K is going to be less than Q, like so, because products over reactants you're adding here, that's going to make that number go up for Q. But we're shifting left, so we know this is going to increase because that's the solid, and so it looks like it's A. The temperature of the flask were to be increased, so we're increasing the temperature. We know heat is over here. It's going to shift to the right. Which of the following identifies what would happen to the amount present at equilibrium? It's going to decrease because it's being consumed a little bit. Well, and we know that temperature is the only thing that can change K. So, and because it's going also to the right, that means because it's going to the right, that you're getting more products over reactants, so that means your K value is going to increase as it shifts to the right due to the temperature change. So the answer would be be there. Okay, more MCQ practice. Strontium iodate. This one's a KSP. Concentration of strontium ions necessary to precipitate out in a solution containing ions at a concentration of 0.10. Okay. So feel like you can figure that out from the KSP. KSP is going to be the strontium times the iodate squared. So KSP, we plug this in, we can figure out the strontium ions. And the iodate here is 0.0, and that would be squared. And then we can figure out the strontium, that would be how much it could have at equilibrium. So anything above that's going to precipitate out. So looks like it would be A. See if we can get to some FRQs here. I don't know how many more MCQs we got. I think that those ones kind of repeat some of the ones we've already done. So yeah, let's get into some FRQs here. So 0.100 mole sample placed in a 2-liter container. So you got to be careful. Now we got to watch that for concentration purposes. This is a 2-liter container, 298K. Eventually system reaches equilibrium. Oh, we don't have the equation above. That's kind of a problem. Calculate the pressure in the container before equilibrium. Let me see if I can find the equation real quick so I can write it down for you guys. Hold on one second.